Okay, so let's begin with this sixth lecture on applied mechanics, applied differential geometry in mechanics. Okay. Yeah. So in the last module, in the last lecture, so to speak, we had begun with a description about mechanics of elastic rods, right? So as I had mentioned that we will be following lectures, particularly by Professor Ajit Kumar, but at the same time, I would also be following notes by other people, by other distinguished people, such as Professor Basil Orderly's work, Orderly's book, in fact, on called Elasticity and Geometry. Okay, this is one such comprehensive material, and then there are books called. So I think I should write it down neatly so that it's easy to follow for all of us. Maybe I'll just write it down here. So I will just call it resources. So number one is essentially it should be Professor Basil Ordel's book called Elasticity and Geometry. It's written in association with Professor White Pomio. Right? And the second material is notes on elastic slender structures. In fact, it is a lecture series which is available online by Ajit Kumar. Okay. And there are several other resources. One such resource is Mechanics of Strings and Rods. So it's more precisely, it's known as modeling. So it's called modeling nonlinear problems. In the mechanics of strings and rods. It's by Oliver M. O'Reilly. There are, apart from this, there are several other good books. Right? Okay, so coming back to today's lecture. So yeah, let's review what we had covered in the previous class. In the previous class, we started with, first of all, understanding the basics of elasticity, where we define elasticity as the tendency of a material to return to its original configuration once the external stimulus or force or some sort of a load is removed. Well, through this schematic, I just wanted to show how it can be graphically visualized. Then we moved on to we wanted to understand the link between how much a body is deforming to, so we wanted to determine how much a body is deforming to the force, right? So it's like finding a relation between force and the amount of deformation. So we first started with a very simple, what you call simple such scenario, which was essentially simple deformation of beams. So we have a so to speak. Okay, I had mentioned about the difference between beams and bars. So beams are elastic structures which can take transverse loads as well. However, bars can only take the loads along its longitudinal axis, right? So this say here this can be either beam or a bar, but right typically we would like to call it a bar since it's right now it's only in extensional load, right? Or load along its longitudinal axis, right? So we have this structure with cross-sectional area, uniform cross-section area as A naught, and its length as L naught. After we apply a load, or in this case, extensional load F, then it extends a bit along the longitudinal axis till it attains something called as a static equilibrium. In this condition, the internal restoring force, so to speak, of the structure is the same as or equals that of the external force. And that's the reason we call it equilibrium and static, because in that condition, the body has it's as if it stays in that situation for as long as is being applied for an elastic material. Right? Now, assuming that we will assume that the length L naught is much larger than the diameter of this circular cross section. So says that the area is very much same. In fact, if not, it's very close to. Of course, it won't be the same, but it's close to uh, the area in the deformed state. So in this case, we've determined the change in length, which is delta L is equal to L minus L naught. And then we compute something called as a strain. So strain gives us a measure of the proportion of deformation, right? So in this case, the proportion of extension, which is delta L by L naught. And we consider the extension to be much less than one, right? So the ratio is much less than one. Next step is to define something called as stress. So stress is just the internal resistance or internal restoring force per unit area. And that is to the external force, right? So which means that F int by A naught is equal to F by A. This is called as sigma, right? Typically in more precise terms, we would like to call it Cauchy stress. Since we are dividing by A, but since we consider A to be very much A naught, right? It's the same as, so we can also it's as if we are referencing force to the original configuration, and then we can call it second polar Kirchhoff stress. Okay. Now, according to Hooke's law, sigma is proportional to epsilon, and the proportionality constant is E, which is also called as Young's modulus. right? And then we substitute the expression for sigma in terms of F and A, and we have E epsilon, right? F pi is equal to E epsilon, and this implies that F is equal to EA epsilon. So this was the Hooke's law for linear extension. Now say we have now let's move to a different, like for example, this structure can undergo three sorts of deformation modes, as we would like to call it. So one is this. Let me draw it fresh here. So say this structure, right? It can go extension F, moments M, and then torsion T. So moment is like you are applying a sidewise force or such that you are trying to bend it, so to speak, right? So that's the reason we call it bending moment. And then you have torsion, or you're applying a torque, right, so to speak. So torque is a moment in plane. So it's as if you are applying uh, a load which tries to rotate this cross section, right, about the longitudinal axis. So that is called as a torsional mode of deformation. So we had determined an expression for the linear extension. Then we move on to do a similar such relation for the bending moment case, where M is the bending moment here, right? And when you look from sideways, so in which case the cross section appears as a vertical line, and then you are applying this bending moment M. So this the more the particular the structure deforms, right? And this deformation, as a result of this deformation, you see that even the center line, or what was the locus of the centroids of all the cross sections, that is what we are modeling as a center line. So the center line is getting bent, right? And once if there is when there is a bending, then of course you would have a curvature, right? Curvature is a geometric quantity here, right? So M is proportional to kappa. And first of all, kappa is equal to d theta by ds, where theta is the angle made by the tangent to the center line with respect to the horizontal axis. Right? And and again, we recall from linear theory that bending moment is going to be proportional to kappa. Right? And the proportionality condition is, or constant is EI, where EI is called as the bending stiffness. Right? So we call this as bending stiffness, the product EI, or sometimes we would also like to call it flexural rigidity. And I is the area moment of inertia, and it's a cross-sectional property. So which means to say that it's a geometrical property. And then we have this linear bending law, which is M is equal to EI kappa, right? Now let's look at the third deformation mode. So this is for a torsional mode of deformation. So in this case, uh, we are applying a torque in the plane of the cross section about the longitudinal axis, and the torque is T. And what it does is it rotates the cross section. Sorry, it rotates the cross section throughout along the length of the along the length of the elastic structure here. And at every location S, we have some sort of rotation of the cross section. So the measure of rotation is given by phi, and phi happens to be the angle between, say, some A vector which was parallel to E1 throughout the structure. I mean, for every cross section. Now, after applying this torque T, A vector will rotate about E3 axis, right? And the rotation will be referenced to with respect to E1 axis, such that the rotation is given by phi, and phi happens to be rotation angle. Right? Now we define something called as a torsion or twist. So twist is given by d phi by ds. Right? Now again, following the linear Hookean law, since Hookean law is by design linear, right? So t is proportional to tau, and then the proportionality constant in this case is gj, right? So t is equal to gj tau, and g is the shear modulus, and j is the polar moment of inertia. And in all the cases, what we have is the measure of deformation, epsilon, kappa, and tau, they all happen to be much less than 1. Right? Okay, so we have established the 3 simple deformation modes, and this is mainly for the such elastic slender structures, in which case it's possible. Then we based on that, now let's define something called let's discuss about beam theories, right? So as we recall, beams are elastic structures, elastic slender structures, so to speak, which can withstand extensional as well as transverse loads, right? Okay. Now, one of the simplest beam theory is what we call as the Euler-Bernoulli beam theory, in which case we have we have some fundamental assumptions which I just put towards the end, but I think I should put it at the top so that things should that we are aware of the assumptions before we discuss the model itself. And I've been trying to put it in a very brief format, since the we are our goal is not to discuss or derive this from very fundamentals, right? Since it's typically covered as a part of strength of materials or solid mechanics. Okay, so the assumptions are that the normal sections to the center line remain normal after deformation. So say you have a segment of a beam, and with this cross section being at an angle 90 degrees with respect to the center line here, is the center line. Then after deformation, this structure is of course going to bend, and even the cross section is going to rotate, right, from the sideway if when seen from the side. And then we see that the cross section is still perpendicular to the center line, locally perpendicular to the center line. So this is what we call as we call this as the Kirchhoff's hypothesis, as mentioned here. And that is a very important aspect of Bernoulli beam theory. And second assumption was that the deformation is so small that the arc length coordinate S, which defines the center line, it's almost equal to Z. So I just wonder, this puts a severe restriction on the applicability of the model, because uh, we would like to have the deformation such that the arc length arc length coordinate happens to be very close to Z throughout, or the Z coordinate, right? And this makes it applicable only for a very small, say, region of strings. Right? Okay. So now what we did is we have this y-axis, z-axis. We have a segment of, or in fact, the say the Euler-Bernoulli beam. We are applying we have this tangent vector t, which is an angle theta with respect to E3 axis. And the central line defines what we call as the planar curve, or we also call it as the neutral plane or neutral axis. Neutral axis. Right. So neutral axis, we call it because that is the central line is neither under tension or under compression. And right, so that is, so it means that the central line is stress free. Now we have this curvature. We define this curvature as kappa z is equal to y double prime with divided by 1 plus y prime squared whole to the power 3 by 2. And for small y prime, we have kappa z, it is just the second derivative of y with respect to z, right? Then we have this bending moment, as we learned from the bending law, we have ei kappa z, ei y double prime, then which gives us the celebrated Euler-Bernoulli beam equation, which is a very simple model, but it is quite powerful in that we can analyze very large structures, including, say, for example, dams and all, right? Based on this simple equation. Now we need to prescribe MZ and the boundary conditions, right? We would want to first define what is MZ, because we would like I mean, since the structure is going to be subjected to several such loads, so we would want to prescribe it functionally, right? And also, to make this problem a well-posed one, we have to provide the boundary conditions at z is equal to 0 and z is equal to L naught. Okay, now let's talk about further extension to this theory, which is called as the Timoshenko beam theory. So Timoshenko beam theory, it relaxes one particular assumption. The assumptions is that the normal sections are still planar, right? Sorry. So the normal extension are still planar. However, after deformation, they are no longer normal to the center line. So which in a sense that we are allowing shearing. Shearing is allowed. And the measure of shear strain is given by gamma. And gamma is called as the shear strain. Okay. And kinematically speaking, we have introduced dy by dz still the slope of the tangent to the center line with respect to the E3 axis. However, we have a new quantity called theta. So theta is the angle made by the normal to the cross section with respect to the z axis, right? So dy by dz minus theta gives us the shear strain, and shear strain is defined as tau by g. Tau is, we call it shear stress. Shear stress is essentially it's essentially shearing force shear force divided by area on which it's applied. Now we introduce some sort of a correction factor K to take into account some of the cross-sectional effects, right? So we have this K here, which is a shear correction factor. We take this just to, since tau is also not continuous, it's not it's tau is does not vary uniformly throughout the cross section. It varies some. I mean, it has some distribution, right? It will vary, say, parabolically as an example, right? So we want so just to incorporate that fact that we want to take it as a mean quantity. So that's the reason we are dividing it by shear correction factor so as to uh, capture the overall um, the mean variation, so to speak, of the shear stress on the cross section, right? Okay. So now we have dy by d theta is equal to just gamma plus theta. Gamma is solely because of shear, and theta is due to the bending. Then we have now in this case the bending moment is equal to ei d theta by dz, right? So we are looking at how much what is the rate of the turning of the normal to the cross sections, and that gives us the Timoshenko beam. These two equations form the Timoshenko beam theory. Now say if there is no shear, right, in this, which gives gamma is equal to 0, then dy by dz is equal to theta of z, and then we see that we are able to reduce the Timoshenko beam theory to an Euler-Bernoulli beam theory. Then we went on to discussing about some fundamentals of strain energy, and this we are going to use quite a lot for both the Rutz and ribbon theories. So okay, so we showed that we are able to define something called as a volumetric strain density, which is E epsilon squared by 2 for a body undergoing extensional load. Now, if we have for a beam of uniform cross-section area A, we can divide this quantity. We can just take V is equal to A dx, dV is equal to A dx, and this is equal to E epsilon squared by 2. And multiply both sides by A. We get du by dx is equal to E epsilon squared by 2, and this is also called as the linear strain energy density. And that the fact is that we have multiplied the strain volumetric strain density with the cross sectional area, and we for the bending moment, for the case of bending moment, the volumetric, sorry, the linear strain density is going to be ei kappa squared by 2. For a torque, it's going to be g j tau square by 2. And if you would like to determine the uh, total energy of a beam of any length L or L, so to then we just integrate the linear strain density with the center line coordinate, with the along the center line coordinate. Okay, so this was a review of the previous class. I just wanted to take a moment to be able to take some time to refresh all that so that we can now proceed to understanding the Cosserat rod theory and Kirchhoff rod theories particularly. Okay, so first of all, let us define what is a rod, right, before we proceed further. So today is lecture 6. So what is a rod? In a most basic sense, we can call fundamentally a rod is a beam-like structure, right? It is a beam-like structure. which undergoes large deformation. But small strains, and this thing is what we call as this makes it geometrically nonlinear. And secondly, as usual, the cross-sectional dimensions are much smaller than the length, than its length. And so, armed with these two facts, right, these two pieces of constraints, right, or rather, if you can call it, yeah, this is the, so that is where it differs from beam structures. So, tentatively speaking, if we can have such structure, the cross section can be anything, not just circular, but circular is just to represent it, just to for schematic purposes. So let this the dimensions be A, the cross sectional some dimension. It can be if it is a cross section, if it is a circular cross section, then A will be say the diameter, and if it happens to be a square, then we can either take the edge or the diagonal, the edge length or the diagonal length of the cross section. If it is a trapezoid, then we can always determine what you call define something called as a characteristic diameter of a cross section. So it's the largest length scale present in the cross section, and this L happens to be the length. Right? So as we learned, A has to be much smaller than L, and because of this restrictions, or maybe the structural uh, so the geometrical features, right? Because of this, what we are able to do is we are able to define this something called as a center line. This will be again loci, locus of all the centroids. Maybe why don't I color in, make it solid line, solid curve. So this is, as we recall, we call it center line. So what we do is we impose, or we rather we lump, right? We lump the cross-sectional properties onto the center line. And we recall that center line is can be modeled as a space curve. So what we are able to do, what we are doing is all the cross-sectional area at any point, says this cross-sectional area, the cross-sectional properties here will be lumped onto the center line at that point, right? So it's as if again, as we recall that we had defined something called as a arc length coordinate for a curve. So from say this center line is located at arc length, I mean coordinate s from its or from its origin here for the center line, of course, center line, of course. Then so we are lumping the entire cross section. So this entire cross section is lumped onto the material point S. And that is the what you call that's what the reduction goes here, right? So once we have this, so it's as if we are studying only the space curve. It's as if we are looking at a one-dimensional body in terms of arc length coordinate. So that is the whole aim of our study here. Now, what we do is let's define the kinematics of our problem. I'll just call it mechanics of rods. Or maybe rod theories because let's look at the kinematics. So we would first begin with an initial configuration, since the body will always be in some configuration before we start applying the forces. Let's put it something like this is this is A3 axis and Ne2, and S starts from here to some point S along the center line. There is some reference configuration. And as you recall, it's a straight rod. We apply some deformation. And here we would have some cross section. Then of course, the center line is located at the position S. Then we have the surface, right? The cross section is the surface. So to define the surface, so if we isolate the surface here, it will look something like this, sideways. And this would be the center line point. Now we would require coordinates to be able to track or to be able to reference the points. Right? So of course, this cross section is a collection of points. Right? So it is a 2D surface. 2D surface. Then we require two coordinates to define the cross section. And what let me do is isolate it, and then let's look at. So it's as if this is E1, this is E2 axis E2 and E1 axis. So here at any point will be reference to say what we call coordinates will be x1, x2. Right, so two coordinates x1, x2 define the cross section. Right. Now what happens is once this rod deforms, then it acquires some configuration, some sort of a bent, twisted configuration, say like this. Because it appears to be thicker, but it should not be the case. So let's just something along those lines. Okay. So we have the center line here as well. So this is our center line. Now at a position S of this, we have this here. So this center line it's like before we are just looking at the deformation. Now the center line here will be I just want to drag it, reference the center line with respect to origin here. Okay. This works. Whatever. Fine, I think this should solve it. Okay, so this gives us the position of the centerline with respect to the origin of the E1, E2, E3 frame. And then when we isolate the cross section here, this cross section, and it will still it's as if this cross section is going to let's put it like that. This cross section here is going to map to another cross section now with d1 vector of S and d2 vector of S. And this is d1 axis and this is d2 axis. And then we have we'll define d3 axis later, right? And this point happens to be R of S, the origin of this. So the origin here was SE3. Now the origin here is R vector of S. Okay. So in a sense that what we have here is that the deformation is defined by R of S and a rotation R, capital R of S. So R of S is the centerline position. And this capital R gives us the orientation of cross section. Right? And we have this so E1, E2, and E3. This is what we call as the Cartesian basis. And D1, D2, and D3. These are all depends on the Archelon coordinate S. They are what we call, as we had discussed quite some time back, I think lecture 1 or 2, I think the second lecture. This is called as the director basis. Director basis or material frame. And sometimes certain books it's also referred as the convected frame because it varies from point to point along the arc length coordinate. So far, so good. So now, in the reference configuration, the rod is defined, or the rod is described as say some x naught of S, and then we have x1, x2 as the coordinates to define the, as I had written it. Let me write this more clearly. So the coordinates x1 and x2 are or the define the coordinate cross sections. The rod with respect to center line, with respect to its center line. This can go. Right? Okay. So in the reference configuration, the rod could be defined, described in terms of S, X1, and X2 as rather I'll call it something like this. So X3 happens to be S itself. And this is given by, so first of all, the center line. We just use the additive property of vectors. So SE3 gives us the position of the center line at for some arc length coordinate S. Then we add X1 E1 plus X2. This will represent, this is the cross-sectional addition. And in fact, we just happens to span the cross section using X1 E1 plus X2 E2. Now let's look at the deformation. Let us take a look. The deformed configuration. Now what happens is this mapping, say we call it let's call it X vector. Then X vector of X1, X2, X3 is equal to S. Since we are mapping all these points, right? This is given as R vector of S is are the coordinates of the or is the Poisson vector of the center line plus X1, fine, X1, then we have D1 of S plus X2, D2 of S. So here you recall something, right? So we make an assumption. So since we're allowing the same coordinates to span the uh, cross section, it implies that there is some inherent quantity, some inherent property or constraint in the deformation. So the constraint is that plane sections or planar sections remain planar, as we had discussed in Timoshenko and Euler bundle in 3, that what you call that assumption still remains. So we do not allow the planar sections to deform. It should remain as it is. Right? And initially we do not, as D1 of S and D2 of S need not be orthogonal, may not be orthogonal. And that is for the very reason that implies that shear deformation of the rod is possible. And secondly, D1 of S and D2 of S are unit normed. Okay. Now we define a third, as we had learned, D3 vector S is defined as D1 cross D2 divided by the norm. Now I'm using norm for the very case that we want to make it divided by norm so that D3 is also unit normed. So this is and right. So of course it as is known from the as is known from vector calculus that D3 is going to be is perpendicular to both D1 of S and D2 of S. So it means that D3 is the choice of D3 is not we are not free to choose it. It does depend on some quantity. It does very much depend on the on D1 and D2. So far, so good. So here is where in this scenario, this forms the these are the assumptions. So I don't know. I think I should put it at one place. Just at one place. So they define the or maybe describe what we call as the Cosserat rod. So far, so good. So we understand what Cosserat rod kinematics mean, right? So this is the kinematics part of a Cosserat rod. And the variation, the difference between the kinematics of Kirchhoff and Cosserat rod happens to mainly in the kinematics. If the kinematics are different, then of course the mechanics is going to be different. Although even if they have similar expressions. However, so Cosserat rod is loosely can be called as non-linear analog, non-linear version of Timoshenko beam theory. Timoshenko beam. Now let's make some constraints. We would very much like to study Kirchhoff rod. The reason, we would make, or in other words, we would want to define or put some more constraints for the purpose of feasibility, and mainly for the from the purpose of say to simplify the rod equation rod further and to make it more mathematically tractable, because and ultimately what we say is uh, it very much, the simplified model also very much mimics or very much represents the reality. So say the additional. So this was assumptions. Now let's look at additional assumptions. So assumptions for Cosserat. So additional assumptions. Or rather than, since additional has a different connotation, let's call it further. So now we allow, first of all, that D1, D2, and D3 are orthogonal and unit normed. And this means that these are requirements for what we call as the orthonormal. So now what happens is, in this scenario, then no shearing of the cross section, or no shearing of the rod. So we have drastically, uh, so to speak, simplified the model by removing shearing of the rod itself. So now what we'll have is that we have this E1, E2, and E3, and this makes it is what we call as the Kirchhoff rod. Just because of this. And then, as we recall here, no shearing of the rod means the planar sections remain planar after deformation, right? Or sorry, cross sections remain perpendicular to the center line after deformation. That's what it is. Okay, now, so okay, so far we have defined Kirchhoff rod. Now let's move on to say how are rotations, or what is R the rotation matrix R. So what R of S does is say, given we have E1, E2, E3, and as we recall, we can use this R matrix here, apply on E1, E2, E3 to get D1 of S. And they are related as di vector of S is equal to, where I is 1, 2. So as we recall, um, the deformation or the deformed deformation mapping. Then we have x vector of x1, x2, and s. This was equal to r vector of s plus x alpha d alpha of s. And now alpha is equal to 1 to 2. These are, and since it appears twice, it means that summation, implied summation, with what we call as the Einstein summation convention. Summation implied, right? And alpha can take values of 1 and 2. And just now we had understood that x alpha and d alpha of s is, and mind you that this alpha, beta, and Greek letters take value from 1 and 2, and the Latin, so the Roman symbols, right, or the letters. I mean, to represent numbers, it can take values from 1, 2, 3. So here we have x alpha. D alpha is r into e r of s e alpha. Fine. So we can just, it's as if can use the linearity property, you'll have x alpha. So it's as if we are rotating right? This represents the rotation of the cross section. And so what we can say is that we have r vector of s. These are the kinematic quantities to describe the deformation. And we make one more assumption now itself, just for the simplification of the problem, is what we call as the further assumptions. It's like we're adding more and more assumptions so that just for simplification of the problem, what we have is the center line is inextensible. Which means to say that the length of a segment of any segment on the center line does not change after deformation. So to speak, that the norm of r prime of s, which is nothing but norm of dr vector by ds, is equal to 1, implying that, and so we take d3 vector of s to be r prime of s. And you recall that d3 of vector is going to be normal to the cross section at any point s. So far so good. And now we, in a sense, that we have been able to very much simplify our process, right, in a sense. So, and talking of little bit about rotation matrix, R vector, this is defined as matrices d1 of s, d2 of s. These are like, you have columns stacked horizontally, or sorry, columns, of course, columns stacked in a sequence. So d1, d2, d3, stacked one after the other, right? And so this is what it is. Let's try to prove it, whether just verify it, whether this is true. So R of S E1 should give us D1, right? So let's just check. So R of E1 is like R of S, something like D1 vector, D2, D3. So these are like, so this is a 3x3 matrix, right? And then we have E1 is 1, 0, 0. So this means that it will be 1 into D1 of S plus 0 into D2 of S plus 0 into D3 of S is equal to D1 of. So we're able to verify this thing, that yeah, this relation really holds. Okay. And likewise, it will be the same for the other two cases as well for, right? Okay, now before that, what we should do is what is try to determine the equilibrium equations. Or what we call as the static equilibrium equations. Right. So we have two different routes. One route is to consider rod as a 3D body and then integrate it over the cross-sectional area to reduce the equations. But I believe that will involve some continuum mechanical principles which we have not discussed in this class. So I'll take the other route where we assume that the forces and moments are acting on the central end of the rod. Right? So we assume that things are all acting on the central end of the rod, and we consider a segment of this rod. So this is, say we have a, so what should I say? We have a large rod, right? And the central line, we extract the central line. So we have this as the body. And there's a rod, so to speak. We extract a segment of this. So from here to this will be S. From here to here, this is like S plus ds. Or rather, let's call it S plus delta of S. Or why not d of S so that we don't have to worry about the simplifications later. So we extract this segment and it's as if we have this point here. So I should just mark this portion as black, and this portion. So we're looking at that portion only. So the distance is ds. I mean, the length of this is ds. Now, what will do is we we assume that this has some internal force N of S, which is pulled by the part for S is, so this I'll write is due to S prime, right? Or S, maybe S prime only, S prime less than S naught, less than S. And on the other side, we have again pulling by this N of S plus ds, right? And this is due to S prime greater than S plus ds. right? And then we also saw that there is some sort of a distributed load here. Let's call it p vector of s, or just say n vector of s, and n cap of s. Sometimes I say that let's use p vector of s. P vector is the distributed load here. Right. Then what the other thing that we have is the moments. Some moment we have here, we'll call it as m vector of s, is the internal moment. And from this side, it will be m vector s plus ds. And likewise, we'll have some local moments, distributed moment called q vector of s. I think we have been able to simplify some of these things. So let's just give them names. So n vector is what we call as the internal contact force. And you'll ask, what is this internal? So internal contact force is the force applied by one portion of the body on the other portion, and that is mainly to hold it. If there were no contact force, say, because we are isolating a segment, the rod, so it's not like it's a free body. That particular segment was being held on both the sides by other parts of the rod. So which means that there is some force which is keeping them together, and that is what is called as the internal contact force. And there is also some moment which is holding them together. We call it internal contact moment. And P vector is the distributed load. It's external load. And Q vector is distributed external moment. This would be force because load contains both, it can imply both force and moments, right? So far, so good. Now let's prepare all that, what we call as the balance diagrams, right? And the balance equations. So say, first we'll start with balance of forces. So what we do is we are looking at static balance, right? So we do not have any time coming the picture, right? So we have n vector s plus ds minus n vector s. But you'll ask me what come minus is there, right? So typically what sometimes is done is you just assume that there is a minus here because we want to find the net force. So we just assume that there is a minus here, some sort of a minus here and well minus here. Otherwise, it doesn't make sense to add them up. Or I mean, since we can only subtract if there is some sort of a we are balancing along some directions, right? So let's say we have this minus here, then plus p of s, and recall that p of s is a distributed load. So since we are balancing forces, so it will be into d of s. Assuming that s, the segment ds is so small that p of s will remain constant over that. So I should also show that thing by aligning it all vertically. Here we can say that is constant over s comma s plus ds over this interval. So, and this will lead us to a value of zero vector because there is nothing more apart from that. Here we use Taylor series for the first term. Taylor series expansion. N vector, this will be is equal to n vector of s plus n vector prime of s into ds plus other quantities, so it's order of ds squared. So this means that we have n vector of s plus n prime of s ds minus n vector of s plus p of s ds plus order of ds squared is equal to 0 vector. And you recall that this cancels out, so we have n vector n s plus and then we can divide throughout by d of s to n vector prime. So it's like 4. So here, so since ds is already small, so like ds tending to 0, it's already differential, right? So overall we'll have just this thing. This is the force balance equation. And the other part was moment balance equation. Balance of moments. So here what we do is we'll have all that things again. S plus ds. This is going to be slightly more convoluted. Plus the moment was q of s ds is again assumed constant over the interval s to s plus ds. Then you'll have what we call as the moments because of this. We'll have some, say, origin, right? And this point is going to be r of s, and the other end will be, this point will be gone as r plus r of s plus ds. Plus you'll have n vector of s plus ds cross, so it happens to be the other way around, cross r of s plus s is cross and s plus ds minus r of s cross n vector of s, plus you'll have this integral as well. And since we recall that uh, this segment is so small that we can just take the midpoint of this Just call it R of S plus ds by 2 cross p vector of S into ds. I mean, this is just because we are taking over a small interval S of length ds, and Ps is almost assumed constant over that. So we'll just apply this some sort of a midpoint rule. Right. So here there will be a lot of simplifications. So let's do it term by term. So this term 1, this term 2, this term 3. So number 1 will be m vector S plus ds minus m vector of S. As you recall, using Taylor series expansion, it becomes m vector prime of S ds plus order of ds squared. Number of point 2, it will be r vector S plus ds cross n vector S plus ds minus r cross n cross of S. Okay, and this is going to be, we'll have to use multiple Taylor series expansion here. First of all, it will be r vector of S plus r vector prime of S ds plus order of ds squared cross n vector of S plus n vector prime of S ds plus order of ds squared, and then minus r vector of S cross n vector of S. Let's take a look. Let's expand it fully. So we'll have r vector of S So here this could have been written as n vector of S plus p vector of S is this plus order of the S is equal to 0. Okay? Then this would imply. So here we have cross n vector of S plus r vector of S cross n prime of S ds plus r vector prime of S cross n vector of S, right? And ds plus all these higher order terms. So order of, we can call it order of ds squared, right? Then minus of r vector of S cross n vector of S. And this term cancels out. So we are left with is r vector of S r vector of S prime Now let's look at the term 3. We'll according to the situation, we'll try to adjust d3, I mean the third term. Let's see how this expression looks like. R prime vector of S plus D Okay, I think this may not give us the answers. Let's just take a look here. Can we write it down as R prime S prime cross P vector S prime D of S ds prime over an interval of S to S plus ds. This is how it should look like essentially. And why not I use this expression here for now, because that's what the true expression would look like. When we would have to simplify this expression actually, rather than that pre-assumed one. So let's see how does this look like. And since this ds is already very small, right? This can be written actually as r vector of s let's see what we can do here. So this we can, let's reformulate this. So we can write this as 0 to some t, or say some epsilon, and then r vector. It's like we are mapping something called s prime is equal to s plus epsilon ds. Right? So at epsilon is equal to 0, we have s prime is equal to s. So that ds prime would look like s prime would look like s is fixed. So it would look like ds into some d epsilon. Right? Yeah. So we are vector. We'll have s plus epsilon ds cross p vector s plus epsilon d of s. And then we have so go from 0 to 1. Then we have d epsilon ds. An integral is taking over place over epsilon, so of course this ds should come outside. And we'll have r of s plus epsilon ds cross p vector s plus epsilon ds, then d epsilon. So here we can use Taylor series expansion r cross, then cross p of s plus epsilon r prime I'm making it more complicated, but yeah. R prime of s into epsilon cross p vector of s epsilon, yeah, epsilon ds plus r cross of s cross p prime of s epsilon ds. There are odd terms of um, ds into d epsilon. Okay, I think we can make some headway here. So this is like ds, then Yeah, so I think we have made some headway here. So 0 to 1, R cross of S cross P cross of S. Then this is going to be d epsilon plus integral from 0 to 1. Let's call it I R prime of S cross PS plus R of S cross P prime of S. This is into epsilon. So ds will be outside again, and then we have epsilon d epsilon plus higher other terms. So what we see here is, yeah, this is where things we were wanted to figure out. This was a very interesting exercise, even for me. We'll put this up here. All this really interests me. So why not I write it fresh so as to be able to understand what we are doing here. So we have d of s, and then we separate, break down into several integrals. So from 0 to 1, r vector of s cross p vector of s. Then we have so with d epsilon, right? So d epsilon plus integral of 0 to 1. Then we have r prime of s cross p vector of s plus r vector of s cross p prime of s. This was multiplied by ds into d epsilon. Sorry, it should be d epsilon ds d epsilon. Then we have all the higher order terms. So we have order of epsilon squared, ds squared. And then we can, this ds can be brought in front of the integral here. Right? And then we see that this law number holds because we are able to, we have been able to do it in a much more rigorous way to show this fact. Oh, okay. So we have ts, and then you know that r of s cross p of it does not depend on epsilon. So this comes out the integral, and we are integrating over d epsilon. So it's just one. So this is like r cross of s cross p vector of s plus. Now this term, what I should call is that, let this be like this, and then we have ds squared. So ds squared and this particular long expression, which will eventually come out to be, just for the sake, this will come out to be r prime of s cross p of s cross r of s cross p prime of s into epsilon into 1 by 2, ds squared by 2. Right? Then we have order of epsilon cubed now, right? Epsilon, sorry, epsilon square and ds cubed. This is like within some integration. So this term will eventually be of order of, so this will be 0 to 1 d epsilon ds d epsilon. So this will be of epsilon square. Epsilon goes away, just like ds cubed term. So eventually what we know is we only retain entire thing as ds r vector of s cross p vector of s epsilon ds squared. That's it. Okay, so what we do is we assemble all of them. So now moment balance equation looks like is Bring everything here, remove this. This was done. Take all of them. Okay. Yeah, copy it. Paste it here. This was our guiding light. And then we have, this implies that this is nothing but this. So copy and paste it here. This is nothing but this. We paste it here. And the second term was gave us this. Copy and paste it here. This was the fourth term. Copy and paste it here. So plus plus is equal to 0 vector, right? Okay, so what we do is m prime of s is fine, ds. Then we have mq vector of s is also fine. Then we have r vector of s cross n vector of s plus p vector of s, because we can add them up, plus r vector of s cross n vector of s plus all adds up to order of ds square is equal to 0. And this, you recall, is nothing but the force balance equation, right? So this is equal to 0 vector because there is force balance. And then we can rearrange everything as m vector of s plus, we can call it r vector of s plus q vector of s. And it's like we are dividing throughout by ds. Okay, so there will be one ds here as well. And then overall we have is equal plus order of ds to 0 vector. And as ds tends to 0, you have a vector of s plus. And this is our celebrated balance of moment equations. Okay, so we have obtained both the equations. So in the next class, what we will do is we will form the energy functionals. So next class, form energy functionals. And then talk a bit about ribbon theory. And with this, the lecture 7 will consist of these two sections. Okay, so I'll stop recording and close this session for today.